Welcome back to the live course. I'm Brittany Brady with O'Reilly Media, and now will be your facilitator for today. A quick reminder, we are recording today's session. We will have it within 24 to 48 hours. You'll receive an email when it's available. With that, I'll hand it over to Benjamin to get started with day 2.
All right, thank you so much. Welcome back to day number 2. Glad you could join us again. Before we begin, just one more question from my end. Do you have any more things you would like to address or discussed before we jump back into the discussion on volumes? So yesterday we left off by talking about volumes and more specifically ephemeral volumes. And today I want to spend, say, 20 minutes or so just to talk about the persistent volume side of things, because it's definitely going to be a little bit different than what we've seen so far. All right, I see no questions. Then I would say we'll jump right in. And I will share my screen. We'll only take a couple seconds. And you should be seeing it now. All right, so let's jump right back in. So yesterday we talked about the ephemeral volume. And we said that to mount a ephemeral volume, we need to define a volume with a specific volume type in our pod definition. We did this primarily with the mtdir volume type. And then we need to provide a mount path to the individual containers that want to actually consume it. Now, today we'll talk about how we can achieve that for a persistent volume. And you can probably already see from the visualization here that that is going to be a little bit more complex. So when we want to use a persistent volume, so a volume where we want to have data stored that needs to outlive a pod restart, or more specifically, when there's any kind of maintenance for your Kubernetes cluster, it should, of course, also persist that kind of data beyond any kind of maintenance that may be happening. So for example, if you were to upgrade a cluster node or all of them, you will likely have to evict all the pods running at the moment before you can go through that upgrade process. And for that purpose, we need to make sure that data, and more specifically customer data, for example, anything database driven, needs to stick around. We definitely don't want to lose that. Now, to basically set up a persistent volume, we need to bring in 2 more Kubernetes primitives. That is going to be the persistent volume kind and the persistent volume claim kind. And you can see here that this claim is in between the persistent volume and the pod or container that wants to use it. So there's definitely a little bit more to the mechanics that we need to understand. So let's talk about what those different resources provide to us and how we need to configure them. Now, before we talk about the individual attributes of the persistent volume and the persistent volume claim, I wanted to mention a couple of words about how we can actually provision that persistent volume. And there are 2 different modes that we can choose from as administrators or even application developers. And we'll speak about who is usually responsible for what here in a little bit. But generally speaking, we differentiate between static provisioning and dynamic provisioning. Now, with static provisioning, we assume that you as the either administrator or as the application developer provision the object for the persistent volume ourselves. So the persistent volume is basically the representation of the object that knows how to reference the underlying physical storage and how it needs to be configured. Now, your job would be to basically create that object, and then later on, you would effectively mount that persistent volume through the claim or bind to it. That's why it's sometimes also called static binding. And lastly, then you need to tie it into the pod later on. Now, when we talk about dynamic provisioning, that would basically assume that we'll leave the responsibility of provisioning the persistent volume object usually to the cloud provider. So that is oftentimes a provisioning method being used in those cloud providers where we already have the right setup in place where the cloud environment knows how to provision that persistent volume for us. with specific performance requirements. So for example, you may want to say, I want a SSD kind of storage to make sure that the data is written pretty quickly and can be read fast. And therefore, we'll leave that responsibility to that cloud provider. Now, there's one more object or type, I would say, like a resource that we need to bring into the mix for dynamic provisioning, and that is the storage class. So storage classes are another resource in Kubernetes, and you can definitely look for those storage classes by using the get method, for example. So if we were to say here in Minikube, give me the storage classes, then you will see that there's already a storage class in place. That is the default or standard storage class that you can see here, which will, in this case, simply just mount it to the host path. So basically just on my host machine to a specific path. But in cloud providers, there could definitely be other kinds of storage classes that are pre-existing and have been set up for you automatically. Now, storage classes can also be created in on-prem Kubernetes clusters, but that is more of a job for the Kubernetes administrator. But ultimately, the storage class has the knowledge to know how to provision a specific storage device, and that storage class would be referenced by the persistent volume claim by name. And I will show you some examples pretty soon. Now, let's first talk about static provisioning here in more detail. And we said static provisioning means we have to create and define that persistent volume ourselves. Here on the screen, you can basically see one persistent volume. And everything that you see underneath the specification section is effectively what we define this persistent volume to look like. And you can see we need 1 GI of storage capacity. We want to provide certain access modes. So access modes basically describe who can write to where. And we'll basically have a look at different access modes in one of the tables coming up pretty soon. And then lastly here, I'm mounting this to a host path. In this case, the underlying host path would be /data/db. Now, just to mention a couple of those configuration options in more detail and how they can be configured. You can see here the access mode can be configured based on the type of access we want to provide. So for example, read-only access or read-write access, and then which nodes we should allow this access for. So it could be for a single node or for many nodes. And then lastly, there's also a new one that had been added a couple of releases ago, which is the read-write once pod that basically provides read-write access mounted by a single pod. Now, you don't have to memorize those access modes. You can always look them up in the Kubernetes documentation. Just wanted to spell them out explicitly so you have a rough overview. And then there's also a reclaim policy, and the reclaim policy basically determines what should happen after the claim has been deleted that was bound to a specific persistent volume object. You can see there are different kinds of reclaim policies. So for example, we can say the existing object should be released and can be reclaimed by a new persistent volume claim, or we could also say that the object should be deleted. There's a deprecated option. They may have removed it in the meantime. I would actually have to check. By the way, there are more than those configuration options, but I want to keep this relatively short. If you do need to look them up, you can all find them in the Kubernetes documentation. So let me walk you through the process of basically first creating the persistent volume, which you can see here on screen. So we basically point our kube control command to the YAML file to create the object first. And then when we inspect that object, as usual, similar to inspecting pods or namespaces or really any other object in Kubernetes, we can find out that the status for this persistent volume is available. So that effectively means that the object has not been bound by a claim yet, so it's still available for consumption. Now let's have a look at the persistent volume claim, so that binding component between the persistent volume and the underlying container. And you can see here that looks actually fairly similar to what we've seen before with the persistent volume. But there's one piece of information that I want to give you here on the persistent volume claim, and that is effectively everything that you see underneath the specification section. You can think of as, I would say, requirements for finding a fitting persistent volume that can fulfill those requirements. So here we say we need to find a persistent volume that has the access mode read write once, and that persistent volume needs to provide us with at least 256 MI of storage capacity. If we do not find a persistent volume that can fulfill those requirements, then this claim would not be able to bind to any of those existing persistent volume objects. Now you can also see here that we spell out a storage class name. And the storage class name, in this case, at least if you wanted to go with static provisioning, needs to be an empty string. Now, it used to be the case that you didn't have to spell out a storage class name, but that changed with a previous version of Kubernetes. If you don't add the empty string here, that value, then what would happen is it would try basically to fall back to the default storage class that I've shown to you on screen before, and will basically dynamically provision a persistent volume object. And that is definitely something we don't want to do, at least in the form of static provisioning. So it's important to have it. You can also not leave it out, by the way. Once we create the persistent volume claim object, we should hopefully see that the status will change to bound, and that is the case as well for the persistent volume object. So that effectively means that this persistent volume could be bound to the persistent volume for consumption. And then lastly, there's only one more portion that we need to put in place, and I already mentioned this kind of type of volume, the persistent volume claim. You can see here we still have the two components, the volume definition of type persistent volume claim. And underneath the persistent volume claim definition, you can see we simply pointed to the name of the object we want to use. And then similar to what we've seen before for ephemeral volumes, underneath the containers section, there's a volume mounts section where you can basically mount it to a specific mount path. So that is basically the static provisioning route. Now let me show you how we can basically use dynamic provisioning instead as well. So as I mentioned before, dynamic provisioning doesn't require you to create a persistent volume object yourself. It would be provisioned automatically by the storage class. Now you can see here on the left-hand side on the screen, there's an example storage class called AWS EBS. And this could be an example for such a storage class that may be available, excuse me, in a cloud provider, in this case, specifically AWS. Now, on the side of the persistent volume claim, we now have to basically assign that storage class name, AWS EBS, to the attribute called storage class name. So what happens at runtime if we were to now create the persistent volume object is that the persistent volume object will be created automatically for us. And you can actually look for it by using the get command, for example. You can see in this case here, the persistent volume object would be created with a unique name. And that name is usually derived of the name of the persistent volume claim, in this case, DB/PVC. And then Kubernetes will basically add a hash to it just to make sure that it becomes unique. So in this first example, we would like to go through the process of creating a persistent volume and bind it to a pod using static provisioning. And that would be exercise number 6 in this case. So I'll give you about 10 minutes for this one. I think it shouldn't be super hard. And I think that's a good way to basically score some easy points in the exam itself. Once you know how to do it, I think you should be good to go. But ultimately, all you need to do is to basically define those objects given based on the configuration they provide to you. And then you are good to go on that end. So I'll give you 10 minutes here, and then we'll reconvene pretty soon. All right, so let's have a look at the solution here. We'll go to number 6, and I'm already there. What I'm going to do here is to create 2 YAML files. Number 1 here would be for the persistent volume. As I mentioned before, static provisioning requires you to create a definition of the persistent volume yourself. And here we will provision 512 MI of storage capacity, this specific access mode, and then the host path is this one. We'll save that, and we'll create the object from it. Okay, so we should have the persistent volume in place, and you can see right now the status is available. And one more thing here, you can see no storage class makes sense because we didn't really automatically provision it using dynamic provisioning. Then what we want to do here is to create the persistent volume claim. And we'll also basically put that in here just by copy pasting it from the solution without having to type it. Most important thing here is make sure that the storage class name is an empty string and that the requested storage here is less than available, less than we provision for the persistent volume. Okay, this has been created. Let's have a look at both objects quick here. So the persistent volume and the persistent volume claim, you should now see that the status changed to bound for both of them. If you were to have a look at the underlying details, you should also be able to find out which persistent volume it actually basically bound to. Which you can actually see here in that column called volume. And then up here, we can also see which persistent volume claim bound to it. So basically how you read this is in the default namespace. And there should be a persistent volume claim object with the name PVC. And there's only one more thing we need to do here. That is the creation of the pod itself. And as you can see here, we're using the persistent volume claim. We're binding to the claim name PVC in the same namespace. And then underneath the volume mounts, we can see that we want to make it available in the container itself at the path var app config. So if we create this pod now, should be able to consume it. So if you were to have a look at the list of pods, let's see if it's running. App will open an interactive shell. And now we should be able to basically navigate to var app config. And then inside of here should be empty as of now. But you can basically create a new file. And this one should be available right here. All right, so that is all we wanted to do. If you want to try out dynamic provisioning at home as a homework, you can definitely do so. All you need to do is to basically go with the storage class that we have in place here. So if we were to have a look at CKAD storage classes, you can simply go with that name specifically with standard. What you can also do is to basically install your own storage class if you want to. I've done this with an open source project. I forgot what it was called. I can look it up for you if you're interested, but it should be part of the list of different labs here. So if you go to the playlist of this guy, and I'm not sure if we can easily go to that playlist, I guess here. I think there should be one for dynamic provisioning as well. And this one is using this one specifically, NFS Ganesha server, which provides your own custom storage class. You can play around with that project as well if you want to get more exposure to dynamic provisioning. But generally speaking, I think you should be good to go with just static provisioning. So here's a question, why is the claim listed as a default PVC? I mentioned that earlier. So default basically refers to the namespace, probably. So it's the PVC object with the name PVC in the default namespace. So that is what that means. So let me also post that here to you. That is the lab for dynamic provisioning if you just want to get a hang of it. So she is mentioning it's not the namespace. Can you give us more information on what it is? If you think it's not the namespace. I would assume it's the namespace, but let me know if it's not. All right, so what do you need to understand for the exam itself? You will need to understand how ephemeral and persistent volumes are configured. And then we can see here that we need to understand different kinds of volume types, mtdir, host path. And we've also seen the persistent volume claim. Just make sure, but they're not necessarily super specific about it, that we need to do static and dynamic binding, or can do that. And we can configure it the way you need it. I would assume for the exam, you likely only need to understand static provisioning, not necessarily dynamic binding, but really that all just comes down to the storage class. So here's a question. If there are multiple persistent volumes with the same storage class, then which PV would be bound to which persistent volume claim? Well, the persistent volume, if you do if you do static provisioning, doesn't have a storage class assigned to it. This would only be for the persistent volume claims. If you see a persistent volume with a storage class assigned to it, let me see what we got here. You will see that it's actually empty, so there could be not multiple bound. If you use multiple persistent volume claims with the same storage class, then a new object would be bound to it with that specific storage class. So maybe that's hopefully more explanatory. By the way, I see all of your questions, whether that's in the Q&A box or in the attendees chat. You don't need to post it into both. I will usually just post it here in both channels. All right. Any more questions before we move on to pods with multiple containers? Here, I will primarily want to talk about different kinds of use cases that are available. We'll probably not go into too much detail here. You will see in my exercises, there are multiple exercises that you can play around with that are pretty involved, specifically when it comes down to implementing specific scenarios. But ultimately here, I just wanted to show you what the need is for multi-container pods, how to configure them, and how you can interact with specific containers in that context. All right, so before we primarily talked about pods with a single container, and I mentioned earlier that we can definitely add more than a single container to the pod as well. Now, what would be the use case here for having multiple containers? Usually you would run your application in one container. And then if you need any kind of helper functionality that potentially runs alongside your main application container, for example, you will want to have a look at the data being produced or logs being produced by your application, and you want to do something with it in parallel potentially, then that would be a use case for wanting to have another container. You would usually not run multiple applications or multiple microservices in one pod, simply for scalability reasons. You definitely do not want to do it. But ultimately, when we talk about those multi-container pods, we usually want to bring in those design patterns, the init container, sidecar, adapter, and ambassador. Some of those design patterns, they may sound somewhat familiar. You may have heard of them by the Gang of Four book, if you've been around in software development for a little bit longer. So adapter and especially ambassador pattern, they have been around for quite a while. And here they just have been basically retrofitted to the context of containers and Kubernetes specifically. Now, the first kind of container we want to talk about is the init container. That's a more specialized init container. Recently, it has also seen some additions to it, which I don't cover here in this course, so we'll want to change that. But ultimately, the init container is another container that is being invoked when you basically start up your pod. And usually this init container will start in the first place before any of the other containers will start. We can use that conveniently for basically downloading configuration files that you may need for your application specifically, or let's say for seeding some data, things like that. Then we have a sidecar. That is the container that I mentioned before that runs alongside your application. By the way, init container will only live for the time of executing that initialization logic. After that, it will be finalized or completed in that sense. The sidecar is another container that runs alongside your application and therefore provides continuous functionality for your application. For example, watcher capabilities or massaging log data or rate limiting, kind of depends on your use case. So I want to mention some of those here in this section. Before we get to the sidecar pattern, just wanted to show you here the init container. So the init container is a container that will be instantiated before your main application container is even being started. So you can think of it as, for example, like a constructor and its logic inside of it that is part of a pod. Constructor, when I talk about a constructor in the context of object-oriented programming. So some logic that needs to be run before the functionality of the class will be made available. Now you can see here we can have multiple init containers potentially, C1, C2. So if you want to separate that initialization logic, you can definitely do it. C1 is basically init container 1, which will be first executed before C2 will even be started. And then only if C1 and C2 are successful, only then will we start the main application container. So there's really no point in bringing up the main application container if any of the init containers are failing. And therefore, that is the execution order you can think of. Do you need to have multiple init containers? No, you can have just a single one, but just wanted to mention that you can potentially have multiple of them. Now, the init containers will be defined in a dedicated section, which is called init containers, separate from the regular containers. So that is how you can basically build a mental bridge here towards the differences between init containers and main application containers as well. You can see here both init containers and containers can define multiple containers with a little dash. So that's a sequence type in YAML, and it allows you to basically define multiple of those containers in each of those sections. Now, when you start up your pod, you will actually see that there's not a dedicated column for the init containers. So under the ready column, you will only see those main application containers, never the init containers. Init containers you may potentially see being executed as part of the status column. And in this case here, you can see we're initializing the init container here, 0 out of 1 being executed. But once they're basically finalized, there's no more indication of those init containers anymore. Now we can talk to individual containers if we have multiple of them running in a pod using the -- container option or the short form option -c. This allows us to effectively basically give the name of the container that we assigned when we created the pod object. And then you can basically use the exec command or the logs command to basically retrieve logs or open an interactive shell or run a command against a specific container. So you can always talk to one specifically. Now here's one example where we spell out one of those container names. Wanted to mention that if you forget to spell out a container name specifically, Kubernetes will try to fall back, or more specifically, kubectl will try to fall back to the what it probably calls the default container. Not quite sure what the algorithm looks like here, but I guess it will simply try to log into the single main application container available. And that is what you can see here on the second line, where it didn't actually spell out the container name that I want to open an interactive shell to. Ultimately here, it will default to web server, which is the only and single main application container. So with that, we will want to give this a try. You will see that this one is a little bit more involved, much longer than the other one. So I'll give you a little bit more time. So what we want to do here is to create a pod with two different containers, one init container and one main application container. And as part of the init container, we want to download a configuration file using a curl command or wget command, probably more like wget in this case, for making it available to your main application container. And you will see that I'm bringing back the content, the content for volumes. Here we will actually want to exchange data between the init container and the main application container. And we'll do that by providing a volume of type empty-dir. So let me turn on my timer here. I'll give you maybe 12 minutes for this one, and then we'll have a look at the solution on my screen. First coffee break for today. Before we do so, let me show you the application in more detail that we want to deploy. If you want to build it yourself, you can actually find it here directly under the app directory. And here there should be a web subdirectory with a Docker file. So this Docker file is basically building a node-based application. And you can see it simply just runs the JavaScript file called server.js. In here, we are creating a HTTP server, similar to what we've seen before. But ultimately here, when we make a call to it, to the root URL context path, it will try to read the file in this location, user shared app config.json. Then we'll try to process that JSON content, and then we'll want to respond with a message here that puts together individual portions of what we read from that configuration file. And you can actually find that configuration file here as well. So if you look at that, you can see it consists of multiple portions. So underneath here, the assumption would be we are providing configuration for configuring the endpoint of a database, for example. And in this case, we have a host name, a port, and a database name, and then we'll put it all together by making it available to the application at runtime. Now, what we want to do here is to basically start with a, excuse me, start with a pod. And the way we can get started with this is by simply using the hybrid approach that I mentioned before. Just wanted to show you one of those use cases where this is applicable. So we know that we need to create a pod, we need to mount a volume, then we also need to instantiate an init container. We cannot easily provide this information just with the imperative command. It doesn't have command line options for all of those configuration options. So therefore, we can get a good starting point, but it won't get us all the way. So what I can do here is maybe I'll just copy paste this. Give me 1 second. I don't have it in my history anymore before I have to type too much. So effectively, we are creating a new pod with the run command. It has the name business app. We are going to use this container image. And then here we expose port 80 and basically write this to a YAML file so that we can basically then further modify it. So that's what we're going to do here. I will then go in and modify this a bit more. And more specifically, based on the information that are provided in the instructions. So first of all, we need to add a init container. So that's going to be added up here. So he will say init containers, we'll give it a name, and then the image, oops, it's going to be busybox 136.1. This one we wanted to rename. By the way, you can also see specific information being added by the dry run command. For example, resources is not necessary. This one isn't necessary. This one probably either, and this one either. So we can actually clean this up a bit more as well. And this looks more like something you would find on the Kubernetes documentation. Then we want to define our volume. And similar to what we've done before, we can add the volume up here or below. The order actually doesn't matter. And we'll give it a name. Name config dir. And the type should be empty dir. As mentioned yesterday, that's an ephemeral volume, but it allows us to basically exchange data between two different pods. And where we want to have it is in both pods. So I will say mount path needs to be defined here specifically. Config dir, and you can see there's a lot of stuff we have to add here to this one example. And we'll simply add the mount path here as well. And now what I can do, I can simply take the same piece of information, go down here and add it here as well. So you can see this volume of type empty dir with the name config dir has been used in both of the containers, so they can basically share data between each other. Now, there's only one more thing we need to do. We need to basically download the configuration file, the JSON file, using a command. And we can do that here by defining command. And then underneath there, we'll simply define a wget command. The wget command will basically download this file, so the raw file that we have on GitHub. I will then place it into this location, so it's going to end up being under user shared app, which is effectively the volume directory. And then the file name will keep. We could rename it if we wanted to, but as you've seen in the implementation of the application, we still want to read from the file called config.json. All right, so we'll create the pod, and hopefully everything goes well. Let's have a look at it. And you can see here, at the moment, init container is going to be executed. That means it will download basically the file. So this may take a couple of seconds before that is done. And now it's running. So what we can do here, exec business app, and see if we can actually find that directory. So var, sorry, what was the directory? Just have to check it again. So directory here in the container was user shared app. And down here, we should now find that the config.json file is available. And you can see it kept the details of it. And what we can also do is to basically see if the functionality of the application works just fine. Here we expose, I think, port 8080, if I'm not mistaken. And as you can see, the main application container can also read from this file now, because it has been mounted using a volume. And then down here, you can see we basically respond with individual portions that we read from that file. So that actually works. So here's a question. Are questions asking JSON format expected in the exam? Can we solve? So the question that you saw here has nothing to do with the definition of Kubernetes primitives in YAML. This is a random configuration file. This is not meant for configuring Kubernetes objects. So that is just something that is being read by the application code. Potentially, you may be confronted with JSON, but you're primarily expected to use YAML for defining your Kubernetes objects. So JSON would not be involved on that end. All right, any more questions on the init container? And when we exit out of here, you can also see that the ready column will only mention the main application container, not the init container in any kind of form. Right, so in the meantime, we will delete that pod. We don't need that one anymore. And I would say now is a good time to take a 5-minute break, and then we'll get right back to it. And then next up, we will talk about how we can also add additional containers that run alongside your main application container. So 5 minutes, and then we'll reconvene again. All right, so let's get back to things. So I want to basically round out this section by talking about those sidecar containers. And as you can see here, in comparison to the init containers, sidecar containers will simply be added to the containers section. And what we do here in this one example, we are adding a transformer container. So basically some helper functionality that will transform data potentially being produced by Nginx or something like that. So the kind of functionality that you want to add here in those sidecar containers is up to you. It really depends on what you want to achieve with that logic. Now, once we create a multi-pod container that has multiple containers defined in the containers section, we should be able to see multiple containers mentioned in the ready column, at least as long as they are starting up properly, of course. But in this case, they're starting up properly, and we are able to see 2 out of 2 containers available in this pod specifically. Now, I wanted to mention a couple of use cases where this may be helpful. And those will be mentioned by the name of their patterns. So effectively, if we're talking about a sidecar pattern here, that basically means we add a second container alongside the main application container. In this case, I just wanted to provide you with one example where the sidecar container, or more specifically the logic inside of it, would look at a volume. And inside of that volume, the application would produce some log files, potentially some error messages that we wanted to capture from the application. And we want to basically inspect if any errors had been produced or potentially based on certain log levels. And then based on that, we will want to send a notification. One good thing about the sidecar container is that both of those containers, the application container and the sidecar container, have individual life cycles. So for example, if something would crash in the sidecar container, maybe the process fails to run, it does actually not affect the application container in any kind of form. Also, one good benefit of separating that logic is separation of concerns. So if you need some helper functionality, we can easily extract that out of your application code. It does not have to be deployed with your application implementation, and therefore can also be reused across multiple pods as needed. Also, if the logic needs to change for the sidecar container logic, then we don't necessarily need to redeploy or change the container image for the main application container. So there are multiple benefits for basically breaking out that logic. and then running it alongside your main application container. Now, there may be other use cases. In this case, that is one scenario where we can bring in the adapter pattern. The adapter pattern is useful if we want to basically adapt to a specific format of a file or some data. Let's assume in this case, we want to bring in an external monitoring service, and that monitoring service expects us to provide, say, JSON data. So it can be properly processed by that third-party monitoring service. Unfortunately, our application writes the data in plain text. So therefore, one logic we could implement is log normalization. So effectively, we could look at the text file and then basically transform it into a JSON formatted file, which then can easily be read by the third-party monitoring service. So instead of basically changing the application logic here, we'll simply just adapt to what we need from an external provider perspective. You can see I have an exercise here. This is a little bit longer, so we'll skip over that. Same thing for the ambassador pattern. There's going to be an exercise, but I'm not going to go through it in my course because each of them would likely take about 20 minutes or so. But take those home as a homework. I think that could be quite exciting. And then lastly, I wanted to mention the ambassador pattern. This is oftentimes being used in the context of network communication. So in this case, the ambassador pattern takes over the responsibility of providing proxy functionality between your application logic and an external service. So let's say we use an external service on the internet, and this external service provides us with functionality that we want to consume from the application. However, we need to provide an authentication token. Maybe we need to provide rate limiting for the amount of calls we can make per minute because we bought a lower tier plan of that external service. Let's see what else. Maybe we need to also provide some specific headers. So all of this logic could be provided into the proxy implementation instead of baking it into the application code itself. So again, separation of concerns, we can reuse that functionality. And the cool thing is if we have two different containers running in the same pod, they can both communicate with one another using localhost. So there's nothing specific we have to set up, at least in terms of networking capabilities. All right, so that's what I wanted to mention about those multi-container pods. For the exam, you need to understand init containers and then the containers section, how they behave and how they are slightly different. You will likely not be confronted with a question that would say, implement the adapter pattern based on XYZ. That's not going to be the case. That's primarily probably just going to be the case that they will give you a pod that runs multiple containers. Maybe you need to interact with one of the containers, not with the other one, and then get some information from it. Or maybe you have to add a init container to it. So it kind of depends on the question. I'm usually not involved in the creation of those questions, so I don't know exactly what they would be asking you about. All right, so before we then transition over to the next bigger domain, and before we do so, I want to talk briefly about what labels and annotations are. I want to ask you if there are any more questions before we transition over more towards enterprise adoption of Kubernetes. All right, doesn't look like it. So if you ever heard of labels and annotations, you probably already know what they are. But you will see that we will use the concept of labels quite heavily in more advanced Kubernetes primitives. And that's why I just wanted to briefly mention it here, what label assignment means and why we need label selection. And then what is the main difference between labels and annotations. So when we talk about labels, we are talking about key value pairs that we want to assign to a object. And this object doesn't have to be a pod. It could be really any kind of object we create in Kubernetes. So it could be a deployment, service, whatever. Now, the labels usually are relatively short, and the reason for that is because we want to use them for searching other objects or for querying other objects or for filtering other objects based on label selection. And I will show you what that actually means in more detail pretty soon. So they're really meant more for a technical capability than anything that should be human readable. So when we compare labels with annotations, annotations you can think of more as the human readable metadata we want to add to a specific object. For example, you may want to provide a contact name or a department name that's responsible for a microservice. That would be a good use case for adding a annotation. Annotations cannot be used for those querying purposes, and therefore the string that we can assign to them can be much longer. Now, there are some reserved annotations that I still want to mention here that will provide runtime capabilities for that object or that can be evaluated by another capability in Kubernetes. And those capabilities I will mention a little bit later. But for now, just think of them as human-readable meta information. So we just talked about what a label provides to us on a technical level. How do we actually add it? There's a imperative label command that we can use with kube control, or you can simply just spell out those labels underneath the metadata section in your object definition. There's a maximum length, I believe, for the value of 63 characters. And we can only use a certain range of alphanumeric and separator characters. Any kind of special characters can usually not be used. Just to show you some examples here, we have 3 different pods, front-end, back-end database, and you can see each of which assign their own labels, so we can potentially search for those objects going forward. Now, those search capabilities do exist on the kube control level using command line flags. So we can basically search for specific objects by providing labels we're looking for. Or they can be used in the form of label selection within specific Kubernetes primitives. And I will give you one example pretty soon. Here's one example for using the imperative label command. So we can add new labels to existing pods. You can see here we are labeling the pod named Nginx with 3 different labels. So we basically just add 3 different key value pairs. And then if you want to inspect those labels, you can definitely do so, either with the describe command, which will definitely spell it out, or with the get command in combination with the --show labels option. Now, at any given point of time, we can also remove the label that we assign to it with the minus sign at the end of the key. That would be an option. You can see it has been removed at the end of this command. Now, probably the more practical solution for assigning labels is to place them underneath the metadata section. And you can see here, we assigned the same kind of labels on the declarative level. There are also some what they call naming conventions or recommended labels. Oftentimes, what we will find is that similar labels will have to be assigned to Kubernetes objects. And instead of coming up with your own naming convention for those very common labels that we want to use, Kubernetes decided to come up with what they call recommended labels. They're not enforced in any kind of form, but those are labels that start with the naming convention app.kubernetes.io / and then a specific name of that label for the key. So for example, here we can spell out what the name of the application should be, what external tool has been used to manage it, what is the version of it, is there a specific component that we're deploying here of a specific microservice. So that is definitely information we can provide. So they are suggesting to you to use those recommended labels, but they're not enforced in any kind of form. So let me show you how we can actually use label selection on the CLI based basis. Now you can see here, if we use the get command, we can provide the -- labels or the short form -l command line flag to search for specific objects that have the assigned labels. And in the first example here, we have a Boolean AND expression where we basically search for two different pods with the assigned labels. You can also search for the key only. So basically find me objects where the key is version and independent of the assigned value, basically provide those objects for us. And then lastly, there's something more complicated here in the third command, where we combine a set-based expression and a basically, what's it called, equality-based expression together in one specific expression here. So basically here we say, give me all the pods where the assigned label is tier front end or back end, and the environment is development. Now, some other Kubernetes objects, sorry, I shouldn't say objects, Kubernetes primitives will actually incorporate label selection quite heavily, not necessarily on the command line tool level, but directly in the specification of the object itself that you want to create. Now, later on, we will talk about a network policy, which is a Kubernetes primitive that lets us define basically like firewall rules between the communication, for the communication between multiple pods. And here we basically say this network policy should be applied to pods that have a matching label to your front end. And there is how you can basically also see how this label selection concept comes into play. So we'll use that quite heavily, and more specifically in the next bigger domain when we talk about deployments as well. So let's briefly talk about annotations as well. As I mentioned earlier, it's providing some descriptive human readable metadata. There's an imperative command called annotation, and then you can also place annotations in the metadata section if you wanted to do it declaratively. Here's one example of some information that are provided here. The author of the microservice, maybe the last commit that we used to deploy this microservice, and potentially the branch that I used to build the container image from. And as you can see here, the usage is quite similar. There's only one major difference. Annotations cannot easily be rendered with the get command, so there's no command line option called -- show annotations, simply because the assigned annotations could be fairly long, I guess, and they didn't want to cut it off. But you can always have a look at it using the describe command. So that is basically how it looks like on the YAML manifest level. So probably nothing too crazy. We'll simply just skip over this. And then lastly, I mentioned before that there are some well-known annotations or reserved annotations that can influence the runtime behavior. In this case, we are using a reserved annotation that lets us effectively define security policies that should be enforced. You can have a look at those well-defined annotations or reserved annotations right here. This webpage basically lists them all. And you can see there are quite a bit of them by now. You will not need to understand those reserved annotations for the purpose of the CKAD certification. But if you are thinking about more advanced certifications, for example, the security specialist certification, that is kind of where they come into play for the most part. Later on, we'll actually talk about one reserved annotation in the context of a deployment. And that is when we will use that in more detail as well. Now we'll skip over this one, do this one as a homework. It basically just lets you use labels and annotations on the command line based level. But I think more important is to basically understand how to use them on the level of specific Kubernetes primitives that have the capability of label selection built in automatically. All right, any more questions on that? If not, we'll transition over to the bigger domain called application deployment. And in here, we will definitely want to talk about scalability and rolling out changes to multiple replicas of deployment of pods. So that is definitely something that's going to be more exciting. All right, I see no questions. So what are we going to talk about here? We'll be talking about the deployment and the replica set Kubernetes primitives, what their responsibilities are, what we use them for, and how they will be created at runtime. Then we'll talk about different deployment strategies. So how do we roll out changes to multiple identical copies, also called replicas in Kubernetes? And then lastly, we'll mention a relatively short section on Helm and Customize. So if we have more complex application stacks, how do we basically build what they call a chart file, at least in the context of Helm, or how do we deploy and customize the configuration using one of those open source tools? All right, so let's talk about deployments here in more detail. So far, we only deployed workload using a plain vanilla pod. Those pods will be placed onto worker node and simply just run. Unfortunately, it does not provide us with any scalability capability so that we could say, well, we need to run multiple instances of that pod now instead of basically it doesn't provide us with that capability, full stop. So ultimately, if we wanted to create multiple identical copies of that application, we would have to do this manually. So we would have to like use the same YAML manifest, potentially change the name of it, and then effectively create multiple objects of it. Unfortunately, if you want to deploy or change the configuration of that pod in any kind of form, for example, you want to roll out a new tag for your container image. In those cases, you would always have to touch individual pods one by one, and that is super tedious. So the better approach for this problem is to use the Kubernetes primitive called a deployment, which basically provides us with scaling and replication features, not only for a single pod, but for multiple pods. And in the context of this concept, we will call this a replica. So pod is effectively the same as a replica, but there could be multiple copies of the same pod definition. Now, when would we want multiple replicas? More specifically, if your application becomes more popular, for example, you started a startup and the startup now sells to 5 customers instead of 1, and you want to have a multi-tenant environment, say, for your Kubernetes cluster, and therefore each customer will have 10 replicas running of the same microservice, and therefore it can handle the workload much better, and more specifically, the network requests coming into your applications. Because having just one single pod will mean having a single point of failure, and that is definitely not something we want to do. Now, with the help of a deployment, we can basically specify how many replicas we want, and the magic happens underneath. Those pods will be created for us automatically. Now, it's also pretty easy to roll out changes. So if you want to update the configuration, or if you want to deploy a new container image tag, that is also pretty simple. We'll simply just change the configuration inside of the deployment definition, and then everything else will be propagated down to the replicas. So how does this actually work? I mentioned the replica set before. So the main responsibility of the deployment is to basically describe what we want to manage. So for example, we want to manage 3 replicas of a pod with a specific configuration. Unfortunately, the deployment itself doesn't understand how to manage those replicas. And that is knowledge ingrained in the Kubernetes primitive called the replica set. So effectively, if you create a new deployment object, it will automatically create the replica set object. And then that replica set object will then instantiate the number of pods managed by that replica set. So effectively, we're just handing down the information. We want 3 replicas to the replica set. And then the replica set is the object that will actually take care of managing those replicas in more detail. Now to create a deployment, we will use the create deployment imperative command. You can see it's pretty straightforward. It almost looks as simple as creating a vanilla pod, but in this case, we actually have the option to provide how many replicas we have by the option -- replicas. If you don't want to provide this configuration option, if you just want to start with 1 single replica, completely fine. It's not a mandatory configuration option. So therefore, if you leave it off, you will simply start by managing 1 single replica, but that number can be changed at a later point of time. So let me show you a YAML manifest for a deployment. You can see this looks slightly more complex than what we've seen so far in the pod definition. You will actually see it's not super complex because everything underneath spec.template is the same configuration we've already seen in the pod specification. So we don't have to relearn anything here, so we can define anything we've learned about before, and that includes the definition of containers, init containers, environment variables, commands, labels, all those kinds of things can be specified there. Now, there's a little bit of more information that we need to provide with the deployment. So you can find under the spec section, there's a replicas attribute, and it has the assigned value 3. And there's label selection again, and that was the main reason why I actually brought up label selection earlier on, because the deployment uses that concept of label selection quite heavily. And you can see underneath the specification section, there's a spec selector match labels. And this label that we assigned here, that key value pair needs to match with whatever we assigned underneath the template section. So make sure that those are the same key value pair, or pairs, could be multiple as well, so that the object can be created properly. It does not work if you use different labels, and I will demonstrate that to you pretty soon. Now, here's one example for having created a deployment object. You can see that listed as the first one here. And then underneath, you can actually see that those objects will be created automatically. So the pods and replica sets, obviously. Again, we see the same kind of naming pattern that we've seen, for example, with the job and cron job before, where if something is being created automatically for us, it will simply just generate a hash and will append that to the name to have a unique name in place. Now, at any given point of time, you can describe those objects, and they will basically tell you what they are controlled by, or what the parent object is. That is information you can find in the output of those commands. Now, I mentioned before that once we have a bunch of replicas in place, we can basically also change their configuration. That would be the use case when we want to add new environment variables, for example, or if we want to update the container image tag because there was a bug fix or feature being built in and released. So therefore, instead of touching each individual pod, all we need to do is to configure the configuration or the template section that I've shown to you in the deployment object. Everything else will be propagated down, and that is super helpful. Now you can see here over time, each of the replicas would be updated with the changed configuration, and that is the default rollout strategy that we have built into the deployment object. Now later on, we'll talk about other deployment strategies that you can configure. But for now, just keep in mind, over time, it will simply update all the replicas. Also wanted to mention that as part of the change that you may make to the template section of a deployment, there is a underlying what they call a rollout history. The rollout history keeps track of changes that we make to the template section of the deployment. And every time we do make a change, there will be a new revision recorded. So any change is called a revision in this context. And why do we want to keep this around? Reason is we may want to roll back or inspect what actually changed between different revisions. You can see here, once we make a change with the second command here on screen, you will see that we have a revision number 2, which we can then inspect or even roll back to, in this case, to revision number 1, if there was some sort of issue in production, for example. So let's say there was an issue in production, we rolled out a new version, but realized that the bug fix didn't work or it broke something else. It's likely a good idea to go back in time. One way to do it is by using the rollout history. And here we can use the rollout undo command to basically go back to revision number 1. And what you can see here is that the revision 1 will be turned into revision 3. So it basically deduplicates those changes. Now you may have noticed the change cause column here. And the change cause column is basically meta information you can provide to a specific revision. So what we can say here basically is that we can spell out why something has changed or what comes with that change. And that is information we can provide in the form of an annotation. So just a couple of minutes ago, I mentioned that there are reserved annotations. And in the context of a deployment, there's the reserved annotation called kubernetes.io/change cause. And that basically provides us with a predefined annotation that lets us provide the information for that change cause. So it's really primarily meant for end users to read what actually changed with that change or with that revision. So therefore, it's something you can add. You don't have to add it, but it's one of the options. And lastly, before we go into the next exercise, I wanted to mention that we can also change the number of replicas controlled by the replica set pretty easily. So let's say we notice that our application, because we're monitoring it at runtime, is getting under load. And the load tells us, well, we are high on memory or we are high on CPU usage. Why don't we just stand up 3 more pods so that we can handle the incoming requests instead? This can be achieved fairly quickly, either by using the imperative scale command or by simply just changing the configuration of a deployment YAML manifest and then applying those changes to the existing object. Now you can see here, after scaling it, it will run 5 different replicas instead of 2. And with that, we actually do want to give this a try to get a good grasp on this concept. And here we want to go to number 11. So this one is probably not going to be super hard. I'll give you 10 minutes for that one, and then we'll show it on my screen afterwards. Do let me know if you have any questions in the meantime. All right, so let's have a look at the solution here. Pretty straightforward. How I usually go about this is to first search for a good starting point. And the way we can do that is by using the Kubernetes documentation. I'll simply use this as the starting point here, and then I will further modify it just to show you how we could operate on this in the context of the exam. So we'll go ahead and say vim deployment YAML. We'll place that in here. And then based on the information that I provided in the instructions, I will change that configuration. So here we want to define a specific key value pair. Here it was tier backend. We want to get started with 3 different replicas. Here we want to use the label assignment version 1. And then lastly down here, we were using 23.0 and pretty much everything else we can keep that way. Before we actually use this definition to create the deployment, I wanted to show you what happens if we wouldn't use a matching label in the template section with the label selector. You will see that it will give us a error message, and it will ask you to basically assign the right kind of key value pair. So therefore, let's go in here, change that to version 1, save it, and then we'll apply it again. And you can see now the deployment can be created. So let's search for deployments, replica sets, and pods. And what you can see here, we are in the process of creating the right pods. So you can see 2 out of 3 pods are ready. Those pods will be managed by the replica set with this name. Currently ready 2, desired 3. And then you can see while we're querying for this, the 3rd container was currently in the process of starting up the container and therefore wasn't ready yet. So if you search for it again, we will see that all of those 3 are now in the running status. All right, fairly cool. Let me do the following. I will show you how the rollout history looks like. So for this pod, I think this was called Nginx deployment. We will see one single revision. That is the first change that we made with the creation of the object, basically. Now what we want to do, we want to change the configuration of it. So let's say we want to go in here declaratively. We want to switch the container image to a different version. So let's say there was a bug fix. I want to update that. So now we want to apply those changes. And we can see that the deployment has been configured. Let's also have a look at the objects in place. And you can see there's something happening that I haven't mentioned before yet, which is the process of updating the underlying replicas. So effectively what happens if you make a change to the template section of a deployment, Kubernetes will create a new replica set object. And you can see that is the new replica set object based on the time it existed for, so 6 seconds. This replica set will be in charge of basically ramping up new pods that uses the new configuration. And at the same time, the old replica set will be ramped down. You can see that we are only running 1 pod at the moment anymore. And this will be ramped down to 0 over time. So while at the same time we create new pods, the old ones will be ramped down. And you can basically also see that here, by the terminating status, which basically tells us this pod will be shut down. So if we now look at this, the end status should be that we have 2 different replica sets, the old one and the new one. The old one will not run any more pods, whereas the new one will run the desired number of pods. All right, so one more thing I want to show you here is the annotation that I mentioned before. So let's say we want to annotate the latest version with a specific change cause. This was called deployment. And you can see that the annotation will be added. You can also add the annotation, by the way, to the deployment YAML file, if that's something that you prefer. And you can see here that the information will be placed in here now. And if you look at the object itself, this information will now be embedded. So let's use the describe command here. You will actually see that the reserved annotation has been added here underneath the annotations section. All right, and one more thing to show you here. We want to change the number of replicas. We can either use the imperative scale command, or we can simply just go in here, edit the deployment object, and change that to 5. and then say k apply deployment. And then that will cause the creation of 5 different replicas. You can see here, the newer ones have a shorter age, so they just have been created 3 seconds ago. And then lastly, it's also pretty easy to basically roll back. So if you want to roll back to revision number 1, you can definitely do that with the rollout undo command. And this one should be deployment. And as you can see here from the rollout history, if I can find that command again, you should see that now we have revision number 3, and this effectively is our initial version of the application. If you were to go back here to the objects that we put in place, you can actually see that the old replica set has been revived, and that is basically the main reason why we keep around that old object. All right, let's see if there were any other questions. So here's a question on the field matching labels is immutable. So basically that means certain fields, once you created the object from that definition, cannot be changed anymore. And what you will have to do here is to delete the object first before you can recreate it. So that's to be expected. All right, any more questions? If not, we'll take the 5-minute break. I think now's a good time. Right at the top of the hour, before we then talk about auto-scaling those replicas. So I'll turn on my timer and then we'll get right back to it. Alrighty, so we have 2 hours left in the course for today. Wanted to mention a couple of words about autoscalers. We've seen that we can easily change the number of replicas manually. However, that kind of assumes that we kind of know how many replicas we actually need for handling the incoming network requests into the application and for basically properly managing the workload. This can only be known if you run some load testing or if you properly monitor the production environment. And therefore, it's somewhat of a guessing game how many replicas you actually need versus what the consumption will then actually look like. Now, the much better option is to basically let Kubernetes decide based on certain thresholds how many replicas are actually required to be created or even be scaled down to. And the functionality that we have in Kubernetes is called the horizontal pod autoscaler. So that's a feature, and more specifically a Kubernetes primitive that lets us define CPU and memory thresholds. And then based on those thresholds, Kubernetes will decide how many pods we will actually need. Now, the information on what the current consumption of resources looks like is managed by a component that is not installed by default in Kubernetes called the metric server. So if you click on this link here, this will bring you to the metric server, which is effectively the component you have to install into Kubernetes so you can basically measure the current usage of resources, and more specifically CPU and memory. Now you can find how easy the installation could potentially look like either through a Helm chart or by running this command here using kube control. And that is basically how it looks like. Let's say we put in place a so-called horizontal pod autoscaler. And this one taps into the live metrics collected by the metric server. It will then scale the deployment, or more specifically, it will tell the deployment that it needs to tell the replica set to scale the number of pods. And based on those thresholds, if we go beyond those, it will basically be the indication to the deployment to basically initiate the scaling capability. So let me show you how this could look like with the help of an example. In this example, we have a deployment that manages a replica set with 3 pods. And each of those pods effectively have to use less than 80% of CPU utilization. So you can define within the horizontal pod autoscaler that the maximum average CPU utilization should not go beyond 80%. So effectively, that means on average, if you look at each of the pods managed by the replica set, it cannot grow beyond those 80% in total. And you can see here over time, that is actually the case in step number 2, where we grow beyond those 80%. And therefore, we need to indicate to the horizontal pod autoscaler, or the horizontal pod autoscaler will indicate to the deployment that we need to add an additional 4th pod in this case. So let me show you one example of how we can define the horizontal pod autoscaler. So as you can see here by the YAML manifest, the kind is horizontal pod autoscaler. There are 3 sections to it. The scale target, so this is effectively the object we want to scale. In this case, a deployment with the name app cache. Then we have a metrics section, and the metrics section defines those thresholds that I just mentioned. In this case, in this example here, I'm only having a look at the CPU utilization, and we set it to 80%. If you wanted to have other metrics here, you can add them as part of the sequence under metrics. And then in the middle, we can also define a minimum and maximum amount of replicas, where we basically say at a minimum 3, but we cannot go beyond 5 at a maximum. So once you have put everything in place, including the metric server, which is a crucial part for making sure that it works, you should be able to see the information rendered here under targets. In this case, I'm only describing the amount of CPU being used. There could be more information depending on what resources you actually defined. So why don't we go through this one exercise? This would be exercise number 12 in this case. Just be aware that you need to install the metric server for this to function properly. If you're using Minikube, you can easily add the metric server using the following command. So if you run Minikube, add-ons, enable, and then metrics server, this will basically install the metric server onto your Minikube cluster. And then once that's available, you should be able to also run the ktop command, which basically gives you the metrics for pods or for nodes, depending on what you want to inspect. At the moment, the metrics are not available yet. That usually takes a couple of minutes. So therefore, give it a little bit of time. And in the meantime, effectively work on the creation of the deployment and the horizontal pod autoscaler so we can have a look at it. All right, so for this one, I'll give you a little bit more time, given that we need to install the metric server as well. I'll give you 12 minutes, and then we'll show the demo on my screen. Okay, so let's have a brief look at this one. So we'll go in and create the deployment in the first place. And I already have some deployment here in place. So let's make sure that we delete this first. Okay, delete deployment. This is from the previous exercise. And that should also delete the remaining objects here. Okay, delete. We'll remove that part here as well. App. Then we'll get started by basically creating a new one. I will say create a new deployment from this definition. One thing I want to point out here that is required for the functionality of the horizontal pod autoscaler to work properly is the definition of resources. So resources basically define the minimum and maximum amount of resources consumed by the application running inside of that container. It's a topic we'll talk about probably more tomorrow, but just keep in mind the horizontal pod autoscaler needs that information to identify where we what the boundaries are basically for resources to be consumed in that container. Otherwise, it would not work properly. So we'll save that and we'll create the deployment. Then let's have a look at the deployment and the object again. Awesome. Then next up, we are going to create the horizontal pod autoscaler. And I'm just going to copy paste it instead of like typing all of that down. It's quite a bit. But you can see minimum number of replicas is 3, max is 8. And then we define the utilization on average to be 75 for CPU. And then for memory, it should be 60%. You can see we're pointing it to the deployment with the name Nginx. We'll save that. Before we create the object, I want to show you one thing. The top command should now work. As you can see here, we can inspect the nodes and their usage of CPU and memory. And we can inspect the pods as well. As you can see here for my single pod that I just created, we are using very little CPU right now, a little bit more memory, but really not that much. So metric server needs to be in place as well for this to function properly. All right, so we created the horizontal pod autoscaler. Let's have a look at the details of that object. And what you can see here right now, it still says unknown. So this will usually take a little bit of time to be populated. But as you can see here, CPU and memory are separated now, given that I provided one single, granted that I provided 2 different resource metrics. Now let's check it again. And you can see after a while, it simply could tap into the resources provided by the metric server and basically reflect those numbers here as well. So if I were to create now traffic onto my pod and would go beyond those thresholds, at that point, the number of replicas would basically change. All right, any more questions on the horizontal pod autoscaler? All right, doesn't look like it. Looking at the clock, definitely want to make sure that we still go through the different deployment strategies that are going to be of relevance. In the curriculum for the CKAD, the CNCF has not been super specific about what deployment strategies you need to understand. I believe they mentioned blue, green, and canary, which is kind of interesting because those are not even built into the deployment concept by default. And they're usually better options for basically supporting blue, green, and canary deployment strategies if you use other projects in the CNCF landscape. So for example, some folks use Flux or Argo rollouts to basically support blue, green, and canary deployments. I will show you how we can potentially set those up with just the core Kubernetes primitives that we have in place. But there are usually better ways how we can solve that problem. Now, the 2 deployment strategies that are directly built into the deployment object are the rolling update. That is the deployment strategy that we've seen in action in, I believe, exercise number 10 or 11. So where basically we have 2 different replica sets, and one will be ramped down on the number of replicas, the other one will ramp up on the number of replicas. Then we also have the recreate deployment strategy. This one works slightly different. It will basically terminate all running replicas first before it creates new ones. And obviously this could cause issues in production, which I will mention in one of the following slides. So let me show you a visualization and how we can implement each of those deployment strategies in more detail. You can see here the rolling update deployment strategy manages two different replica set versions or objects in this case, and will basically manage those objects based on those replica sets. There are, by the way, more configuration options that we can configure in the deployment object. So far, we haven't really set any of those configuration options. It simply just went with the default strategy, which is rolling update in this case. Now we can decide to also tweak the number of pods that we want to be shut down or made unavailable. That is configurable with those options that you see here on screen. But by default, I believe the number is simply just 1, and max unavailable is 0 in this case. There are different pros and cons, so benefits that we have with each of those deployment strategies. So it kind of depends on what you, how you want to roll out your changes. With the rolling update, we basically do not get downtime usually. And the way we basically update those changes is by bringing up a new replica while at the same time shutting down one of the old ones. Now, this could cause an issue if we were to introduce breaking changes for APIs that we expose to consumers. So for example, let's say your microservice that you're updating changes the signature of an endpoint as a breaking change without being backward compatible. In the process of updating the existing replicas, there could be an issue where some consumers will hit the old version, some consumers will hit the new version. And if that is not backward compatible, this is likely not a good strategy for your purposes. Now, the recreate deployment strategy, as I mentioned before, will simply just shut down all the old ones, and then we'll bring up the new ones at the same time. And you can see here that the strategy can be configured by simply assigning the type recreate. I believe there are no more configuration options for that strategy specifically. I would say the recreate deployment strategy is a good option for your development environments or staging environments, not so much for production in the first place, because it usually causes downtime because we will shut down all the replicas that are currently running, and then only then we will create new replicas that run the new version. So therefore, if we have consumers in a high traffic application, they will likely hit a 404 or some error message, depending on how you have that configured. Blue-green and canary deployment strategies are super helpful if we wanted to create some experiments or if we wanted to create some additional redundancy. So blue-green is super useful if you want to run the old and the new version at the same time, and then want to run some additional testing against the newly deployed version before you actually make it available to end users. You can see here in this scenario, we basically do not allow to route traffic through that service object to the old version anymore. We already switched over to the new version, but ultimately you can decide how traffic routing should look like, but you will never run into the case where the old version is being shut down and then the new version does not work for whatever reason. So that is a good option if that's something that you're trying to solve. How you would solve that with plain old Kubernetes is by simply creating two different deployment objects, which then of course means we create more resources that we need at the same time. We will also have to take care of network routing configuration. So depending on which version you want to route traffic to, you will have to change the configuration of the service object. And then lastly, canary is useful if you want to run some A/B tests. So for example, let's say you introduced a new feature and you want to see how that feature is being received by the end user. What you could do here is to set up another deployment, but for this deployment, we configure it to only run a much smaller number of replicas. because then we will only want to route traffic to the new version of the application for a subset of users. So that is something that you could configure with the service or load balancing and specifically. So there's probably a little bit more involved here, but ultimately that's a good option for basically trying out how features work out, if they fulfill the requirements, if they're well received by end users and things like that. But ultimately, again, you would create 2 different deployment objects and you would then configure the number of replicas with a different number. So I would say do this as a homework. Effectively, in this exercise, you would create 2 different deployment objects and then change the traffic routing through that service. Given that we haven't talked about the service yet, I would say either try this out at home or come back to this one. It may be important to the exam, but it really combines multiple Kubernetes primitives, including the deployment and the service, which need to go together in this scenario. So I would say for the exam, just make sure that you understand how the deployment concept works and how it delegates the responsibility of managing replicas to the replica set. We've seen that we can scale the number of replicas later on, either manually or through a horizontal pod autoscaler in an automated fashion. We've also had a look at the revision history. And then lastly, we briefly explored some of the more common deployment strategies. All right, any more questions on the deployment specifically? If not, we'll talk about some additional open source tools that we can use to basically deploy applications that not only involve one single primitive, but multiple of them that can look fairly complex, and there are external tools that can help us more specifically Helm and customize. I'm just going to give it a couple of seconds to see if there are any questions popping up right now. If not, we'll move on to the next topic, which is going to be on Helm specifically. All right, I didn't see any questions. So I would say let's just press on. We have about 20 minutes left before the next coffee break. So maybe we can talk about Helm and customize within those 20 minutes, and then we could be done with that bigger domain here. Now, so far, we primarily used kube control to effectively manage objects in Kubernetes. Now, obviously, this could be fairly tedious when you think about the number of objects that we need to manage. So far, we only touched on namespaces, pods, replica sets, deployments, horizontal pod autoscaler. I think that was about it. But later on, you will see that if you want to run an application in production, that you will need far more Kubernetes primitives and objects that need to be created for your application stack to run properly. We're not necessarily just talking about one single microservice. Oftentimes, they go together. And therefore, managing each of those YAML manifests using kube control could be fairly tedious. One of the tools that emerged out of the need to better manage application stacks is called Helm. So Helm lets you basically install a set of YAML manifests fairly easily, while at the same time making it configurable at the time when you deploy it. So let's have a look at how that actually plays out. So oftentimes when you look at Helm, which you can actually see here, helm.sh, they categorize themselves as the package manager for Kubernetes. I would probably not describe Helm as the package manager for Kubernetes specifically. It's one of the features that we have with the help of Helm, but it's really not really one of the main purposes. It's one feature that we can use and will use, but there's far more to it. So how I basically describe Helm here is that it allows us to effectively install a set of objects with usually one or multiple Helm commands fairly simply instead of having to use kube control anymore. So instead of using kube control, you would be able to use the Helm executable, which is a executable you have to install onto your machine. So if you go here to the documentation and go to introduction, I believe installing Helm, you will actually find the corresponding installation instructions for that executable. Well, I already have Helm installed on my machine here. So if I were to run Helm, we'll see it's available. And I could, for example, say Helm version, and it will give me the current version of my installation of Helm. Currently 3.17.2. I believe we're getting ready for version 4, and therefore this version will change pretty soon. So ultimately, what we would do is to use the Helm executable to effectively install what they call a chart file. So the chart file is basically just a archive file that contains those YAML manifests that you want to use to deploy your application stack or something else that has been produced by somebody else. Now, this chart file can either live locally on your machine, or you can pull it down automatically from the so-called central chart repository. So that is the location where you can search for existing chart files that have been produced by somebody else and reuse them. And there are very popular charts available already. For example, if you want to manage your Kubernetes cluster with Prometheus and Grafana, there's a chart for that. Let's say you want to install PostgreSQL, that's available as a chart as well, and many more. The example I'm going to go with is going to be the Jenkins CI server, which is just another example that's available from there. Now, we can have a look at that chart repository, and you can see this is the URL. They sometimes also call it Artifact Hub. I think that's the official name. But if you were to search for, say, Argo CD, you will likely have hopefully just one hit, but there are multiple distributions apparently from different folks. But that is pretty much how we can potentially install Argo CD pretty simply by using Helm. So let's say we wanted to install the the Prometheus and Grafana stack onto our machines. We can select one of those charts and effectively get the installation instruction by simply pressing this install button. So with Helm 3, there are two steps that we have to go through. One is to basically tell your local installation of Helm where to find the Helm chart file. Keep in mind, Artifact Hub is basically not hosting those artifacts. It basically is just a UI on top of what's available. But the actual artifacts or the chart file lives in this location here. So you will have to add that to your Helm installation. And then you can use the install command to effectively install the chart file with a specific version. And then what happens is it will basically create all the different objects that are part of that chart file. Now, how do we know what kind of objects will be created? We can have a look at the templates section here. And in the templates section, there is a list of resources or objects that will be created here. As you can see here, different kinds of objects like a network policy, service secret, and many more things here that will be created once you install the chart file. So if you want to do this manually, this would be super tedious. On top of that, you can also see that those YAML manifests for the objects to be created look slightly different than what we're used to. Now, one feature of Helm is to use a template engine to make this definition of an object more configurable. So for example, here, you can see that we can configure the namespace or the name that should be used for that secret. So those kinds of values are completely configurable. And not only do we replace individual variables, but you can also see that the templating engine also has more complex constructs here. For example, a while loop and things like that. So those are built-in capabilities within Helm. Now you may ask yourself, where are all those values coming from? So there's a list of default values. So if you click on that default values button, it will give you all the defaults here that are predefined. So you don't necessarily have to set them. This list is extremely long, 5,000 lines of code. But you can override them on the command line if you wanted to. Okay, so that's a quick rundown of what Helm actually does. What do you need to understand for the purpose of the exam? So for the purpose of the exam, all we need to understand is how we can search for existing charts, how we can set the repository for that chart we want to install, how to install the chart, and then what the effect of installing the chart basically is, and then ultimately likely to uninstall a chart as well. Let me show you how we can achieve that using the Helm executable. And just be aware that the documentation page for Helm is available and is a valid documentation page and URL for the exam itself. Now you can see here that we can not only find charts using Artifact Hub with the search bar, but we can also use the search command, as you can see here. So we can say, Helm, please search for any chart files with the name Jenkins and make them available as a search result. So what you will get back is the different kinds of URLs for chart files that we can use and the corresponding versions. Now, I already showed to you that we can basically add a repository and make it known to your local Helm installation. This can be achieved using the repo add command. So basically here we provide a URL and a name for the repository. And then lastly, we will simply say from this repository with the name Bitnami, we want to install the Jenkins chart file with a specific version. So that's effectively what we've seen already from the Artifact Hub webpage. Now, once we installed the Helm chart, we can also search for it. So we can list them using the list command. And we can also inspect the pods and other objects that will be created by that chart file. So by running the install command, you will basically have created multiple objects depending on what's included in that chart file. And then lastly, here's one example for the uninstall command. So uninstall will not only uninstall the chart file, but it will also delete all the objects managed by that chart file. All right, so I see there is one question here. Or comment, Bitnami is no longer open, so basically useless. Perhaps change the slides for the next course. Yeah, I can do that. Thank you so much for the pointer. I believe I should probably also change it in my book going forward. I hadn't realized that. I didn't look at that recently, but somebody I think mentioned it before. I had read about it before. So thank you so much for the comment. All right, so that is what we wanted to look at here with the Helm executable. I would say do this one at home. It's not super complicated given that we are just trying to install an existing chart. And you can basically find all the information directly on Artifact Hub. So effectively, if you want to install something, run this command, and then you're basically done. That's all there is. By the way, you can also build your own chart files, but that is going to be out of scope for the exam. So if you want to use Helm for deploying your own application stacks, you can definitely do so. And the way we do that is part of my slide deck. If you're interested, I'm not going to talk about it, but you can see it's following up here in my slide deck. So if that's something that you want to get a head start on, definitely check that out. I will go forward and will not talk about that in more detail. One more side note that may be important to you when you install Helm charts is that we can effectively set or override those default values that I mentioned before. So if you want to do that, you can use the --set command line flag to basically provide one of those options, which will then be overwritten. All right, so they also mentioned Customize here, and Customize is another open source tool that emerged out of the need to basically manage application stacks or to install operators in general. We will still talk about operators probably more tomorrow. We'll see about that, but ultimately that is another tool you can choose from. If you compare Helm with Customize, you will notice that Customize does not require you to learn a new templating engine. So therefore, some folks like it better than Helm, but that is really more a personal preference. So what exactly is Customize? So effectively, Customize can also be used to install operators and or application stacks. One of the benefits of Customize is that we don't have to bring in a templating engine. And how it works at runtime, if you want to modify the configuration of those YAML manifests, is that it will basically merge in changes to your manifests as you define them. Well, the cool thing also is that kube control already has support for Customize built in. So if you say here, kubectl Customize, you will see there's a built-in subcommand or command, it's not a subcommand, into kube control directly. Now there's a separate executable if that's something that you want to install, but ultimately it is built into kube control, so you don't have to necessarily install something else here. So let me show you what we can actually solve with the help of Customize. So oftentimes Customize is, I think, at least that's a personal preference, is more convenient if you don't necessarily want to install an operator, but you want to manage your own application stack, and you will want to manage that and customize it going forward. So for example, you don't want to bring in a templating engine, you don't want to convolute your manifests that you check into version control with specific notation for that templating engine, and want to keep them as such. So how Customize usually works here, instead of creating a chart file, it basically lets you build a set of YAML manifests locally from a plain old list of YAML manifest files. You can see here that the deployment and the service we want to basically install into your cluster is going to look exactly what we've seen before. Specifically, the deployment, we haven't had a look at the service yet, but ultimately that is what it boils down to. And then there's one more file that we need to add called customization.yaml. This file is basically the file that contains the rules. So basically, how do we want to customize or configure the YAML manifests even more? Now, there are different options that we have here that we can add to the customization file. We can define which resources we want to customize. Those would be defined under the resources section. Then we can even generate new resources based on specific generator functionality. So for example, we could generate a new config map based on data that we find somewhere else in the file system. We can transform existing YAML files. So what do we want to do with the resources listed underneath the resources section? And then there's also a validators section that can validate specific transforms. So let me show you one example or multiple examples for that customization file. Here I'm trying to keep it as simple as possible. In this example, we want to automatically add labels to all the resources without having to spell them out individually per YAML file. You can see under resources, we mentioned the deployment and the service YAML file. And then on top of that, we define a set of labels which will be added automatically to those objects when we create them. Now, instead of manually creating that customization.yaml file, you can also generate that file as a good starting point. There is a create command that is built into the customize executable or the subcommand or command within kube control. That basically achieves something similar to what I've shown to you in the previous example. And then I want to show you two more commands. One is the command for basically getting a preview or a dry run of what would be created at runtime. This is something we can achieve with the build command. So the build command lets you build the resources based on the rules you specified in the customization.yaml file. In this case, you can see here that we added those labels. And then lastly, of course, we want to create objects from our set of resources. We can do that with the apply command and the -k command line option. Now you can see here, it will basically create the deployment and the service for us, including the labels and so on. Now, one use case that people like Kustomize for is the ability to basically easily manage multiple different kinds of environments. So let's say you have different Kubernetes clusters per environment. Let's say you have a development environment, a production environment, and a staging environment. And you don't necessarily want to have a complete set of copies in the form of YAML manifests for each of those environments. Because imagine, let's say you wanted to make one change, then you need to make the change across all those different copies. So there's a much better way to achieve that using Kustomize by basically have a common configuration, which are placed under the base directory, and then individual customizations that only apply to one specific environment. So you can see here for the development and the production environment, we have specific customization files, which will then add on to those customizations. So let's have a look at one of those customization files. So in this case, for production, I'm referencing all the resources in the base directory. And then what I do here as well is to basically add a specific namespace, a name prefix for all of the objects I want to create, a generator for config map. So that will basically create a config map on the fly by looking at the values within the config.properties file. And I also want to mix in a specific configuration for my deployment. So for example, in production, I may want to use 10 replicas, where in development, I may want to use 2. So that is definitely something we can achieve here. And then you can build it with the same kind of commands that I mentioned earlier, either build or the apply command. Pretty straightforward. So you may ask yourself, what are the benefits of Kustomize, or how does it compare to Helm? It really depends on your use case. I would say there's not a better option. It kind of depends on the scenario that you want to fulfill. I oftentimes like to use Helm if there's an existing Helm chart file, and I can easily install that onto my Kubernetes cluster. But I do prefer Kustomize when I want to manage my own application stack and want to further customize that. Now, when you look at Kustomize, I already mentioned some of the benefits here. For example, it's native to kube control. We don't have to necessarily install an additional executable. We don't have to copy paste the base configuration multiple times if you wanted to manage multiple environments. You have to learn a new templating engine and basically the notation for it and many other things. So if that's something that you want to play around with, I would say do this at home. This would be the exercise, generating a secret and patching a deployment with Kustomize. I think that gives you a first taste on some of the features of Kustomize. Generally speaking, if you wanted to have a course or the full-fledged set of features being laid out in exercises and a course, I would suggest join a different course that's dedicated just to Helm or just dedicated to Kustomize, or both, because we could easily spend 8 hours on those feature sets. The features are pretty vast, and we could probably go through 10 or 20 different scenarios for you to fully understand those tools. So therefore, we'll keep it fairly light on that end, and that is also the only thing that you need to understand for the exam. So keep that coverage relatively light, know how to run certain commands. One more side note, the documentation for Customize is available here. And you can find it directly inside of here, which basically walks you through it. Here's a comment. Also, both Helm and Customize were introduced in the CKAD exam. That's correct. There, the angle is slightly different. There, they just want you to understand how to install basically a chart file or an operator, basically. But basically, the commands that we talked about are the same. So coverage is actually kind of similar in the CKAD for this. All right, any more comments, questions before we take a 5-minute break and then transition over into the next bigger domain called application observability and maintenance? All right, doesn't look like it. So I'll turn on my timer. And now would be a good time to get another coffee before we enter the last hour of the course for today. All right, so we have about 55 minutes left for today. So I definitely want to make some progress here on the next bigger domain, application observability and maintenance. For the person that was asking me about the voucher discount code, I just posted into the attendees list or attendees chat, sorry. And there you can get 30% off. I just needed to talk to my contact at the Linux Foundation, and they were so kind to give me also a 30% off. So if you need a code now, that would be valid at this point. All right, so what are we going to talk about here in this section? We will talk about API deprecations. So what actually happens when the Kubernetes project decides to deprecate a specific API or a primitive? How do we handle those situations, and what do you need to do on your end as an application developer? So we'll give you some techniques here on how to manage it and where we can find more information about the API deprecation in the official Kubernetes documentation. Then we'll talk about container probes. So how do we verify the health of our application running inside of the container? There are different kinds of probes that we can specify for a container. We'll talk about all of them, and we'll mention their use cases as well. You can see that the metric server kind of falls within the same section here. So given that we already talked about that, we'll probably keep it super light. And then lastly, I also want to mention a couple of things on troubleshooting pods. So if something goes wrong, how can we basically identify the root cause, and how do we fix the underlying issue? So that's what we're going to talk about in this section. And I want to talk about the API deprecations as the first topic here. So that is a topic that had been added maybe with the last update of the curriculum. What they want you to understand is that Kubernetes releases a new version 3 times a year. And then based on that release, they may introduce deprecations. So deprecation basically means we mark a specific feature or Kubernetes primitive in the API as deprecated. So that means it's scheduled for removal or replacement with a later version of Kubernetes. Now we can find out about that deprecation policy and what it means, how it's being handled here with that link. I'm not going to go into that in more detail, but ultimately the result, or what happens to you as the application developer that creates objects in Kubernetes, is that we usually receives a warning message when we try to create an object that has already been marked with deprecated. So it's usually a good idea to do something about it, not to leave it hanging. Don't ignore that warning message, because as soon as your administrator tries to upgrade to the next version of Kubernetes, you run the risk that you potentially use a API that's not available anymore or that has been replaced by something else. So therefore, make sure that you manage those deprecations. Now, there is a deprecated API migration guide. If you click on that one, you will actually see what will be removed with a release of Kubernetes. So for example, here with 1.32, you can see the list of changes that came into play. There were actually more changes with earlier versions of Kubernetes, so you can have a look at that historically. But that's a good guide to have to really understand what is going on. Now you can see here that we can also use the API versions command to identify what APIs we have available. And I can actually do this exactly here as well on my machine. Sorry, not API resources, API versions. So you can see those are all the APIs that we currently have available from within your Kubernetes cluster. Sometimes you may even see that there are different versions, like version 1 and version 2 for the same kind of API set. That is probably just for backwards compatibility reasons. At some point of time, they will likely just remove version 1 here. So let me show you some scenarios on how this deprecation warning message could play out. You can see here we have the deprecated API autoscaling version 2 beta 2. And that was a API version that was available in pre 1.23 of Kubernetes. They did mark it as deprecated with 1.23 of Kubernetes, and then finally removed it in 1.26. Now, if you were to be on Kubernetes 1.23 or higher, but lower than 1.26, you would usually see that warning message that I mentioned before. So in this case here, we get the warning message that the horizontal pod autoscaler and the API version that you defined here will be deprecated or is deprecated and will be removed with version 1.26. So what do you usually do about this? You would effectively go to the documentation and try to find the relevant portion inside of it that tells you what you should use instead. Now you can also see there's a little hint here what you should do on the command line. You could use that as well, but if you want more context, if you want more description of why that has been changed, have a look at the official documentation. So effectively, you would switch here to autoscaling version 2. Now, under certain conditions, it's also possible that certain APIs get completely removed. This may be the case if your administrator basically jumps multiple versions when he or she upgrades the Kubernetes cluster. So let's say you upgrade from 1.23 to, or 1.22 to 1.32. In this case, you will likely notice that the API that you're using for an object doesn't exist anymore at all. And that is kind of a little bit unfortunate. So due diligence will have to be done before you actually upgrade your cluster as well. Now you can see here that the error message is not super useful. It simply just tells us that it doesn't know what we want to create here. That is really just the result of the API not being available anymore. So it's kind of confusing when you see this error message because it makes you doubt that you're actually using the right kind or if you have a typo somewhere there. And then lastly here, there's a replacement which you can also find in the official documentation. And with that, let's give this a try. We want to go to exercise number 17 in this case. where I already set up 2 different YAML files, and I want you to basically try to create them. You will likely see a deprecation warning, or you will see an error message. We will have to fix it up based on the techniques that I mentioned earlier. So for this one, shouldn't be super hard. I will give you maybe 10 minutes, and then we'll talk about the solution on my screen. All right, so let's have a look at the solution of number 17 here. So we'll go into that exercise because I already have those files right there. And what I'm going to do here, I'm going to have a brief look at what we got. So we have a config map.yaml and a deployment.yaml. We haven't really talked about config maps yet, but that is definitely something we'll explore sometime tomorrow. But what we'll do here is to say k-apply -f, and what you can do, I didn't mention that explicitly, you can basically apply all the changes in the current directory and any YAML file that you can find here using the dot notation here. And we can see that there is an issue with the deployment specifically, but it looks like the config map has been created properly. So config map probably does exist now. And it does exist. So we have the data config, but we still need to fix up the deployment.yaml file. So let me do the following. I'm going to go in here, and we can see here that app version 1 beta 2 does not exist anymore. We'll fix that. I believe that was probably rendered here somewhere. It was not rendered. It just says that it doesn't find it. But if you were to go into the documentation, and let me take this portion here maybe and go search for it, you should be able to find something here in that migration guide specifically for the deployment. As you can see down here, migrate manifests and API clients to use the apps version 1 API version, and that was effective since Kubernetes 1.9, so for quite a long time. So therefore, we fixed that. So let me run the command again, see if we patch everything up. Looks like it knows that the deployment does exist now. But on top of that, we do need to fix up a couple of other things. So apparently, the label selector was not part of an earlier version of that API. And therefore, we need to introduce that on our end now. So something's missing here. It tells us that the selector does not match what we have in the templates. In fact, there's actually no selector here in place. We have the template section and the label assigned here, but we need to basically put a label selection here. And how this looks like, I would usually go to deployment and have a quick look if we can find something about it. And you can see here selector, that is the portion that we need. So I'm just going to copy paste that into here. Just need to make sure that the assigned key value pair is correct here. So that would be run and with the value app. So let's see if that actually fixes it. And still not. Field is immutable. So let me see what I did here. So labels run app, selector match labels run app. That looks good to me. Not quite sure. Let me have a look at the. Looks like I already have a deployment running. That's probably the issue. Let me wipe that out. This is probably from the previous exercise, k-delete deployment. Just something you need to know. We try to update effectively the existing deployment, but we can't do that for that field specifically. And as you can see here, we now could create that deployment specifically. So that's a typical question that you could potentially get in the exam where you have to fix something up, and we need to identify how we have to fix it up by using the migration guide, which is super useful in this case. So here's a question on K-explain. I will get back to you. So let me do the following. We'll make some more progress in this domain, and I will answer your question during the next exercise that we go through. It's likely potentially going to be even the last exercise for today anyway. But before we go into your question, I still want to make some more progress here on the content so we don't spend too much time on that. But I'll get back to you pretty soon. All right, any more questions on deprecated APIs? If not, we'll transition over to those container probes, what they are, what we use them for. All right, doesn't look like it. Obviously, once we deploy something to production, and when I say something like a pod that runs at least one container within an application, things can go wrong. Now, you should put monitoring in place, nevertheless, independent of the feature we're going to talk about. But ultimately, things will go wrong. Nothing will ever go down the happy path all the time. But thankfully, there are some features in Kubernetes that can help us with mitigating those situations at least. And the feature that I want to talk about here are the so-called health probes or container probes, which are effectively, you can think of them as mini processes that run in the background that will check your application for certain conditions. And if a certain condition has been detected, we will basically identify it as failed or as successful. Now, effectively, the mini process that I mentioned here is being run by the kubelet cluster component. So that is the portion responsible for basically making that verification. And there are different kinds of verification methods we can choose from. For example, we can run a HTTP GET request. That's a good fit for a web-based application. And try to open a TCP socket connection and other things. I will actually mention them pretty soon in one of my slides as a full example. Now, there are 3 different probes that we can define for any container. We can define one of the probes for one container or all of them, doesn't really matter. You pick and choose dependent on the verification that you want to run here. The first probe that I want to mention is the so-called readiness probe. So the readiness probe verifies if the application is up and running. And therefore, in the time between starting up a pod and having a functional application running inside of the container, really doesn't make any sense to route any network traffic towards that container because it would just give you an error message or failure of sorts. So therefore, we can put the readiness probe in place just to make sure that we hold off on any traffic reaching your container. So that's exactly the reason why you may want to put a readiness probe in place. And we also have the liveness probe, and the liveness probe is useful for applications that are running for longer already. So once we have a running application in the first place, we also want to make sure it's still running in 5 minutes, 5 hours, 5 days, and so on. For that purpose, we can run the verification against the running application as well. And in case an issue is detected, the kubelet would automatically restart the container. So if you have an application that fails for various reasons, for example, you run into a deadlock or a memory leak or something that fails in general, then this would be a good option to basically put that into a working state again. I would say that is not the end-all, be-all solution to that problem. You will still want to have a look at your application code and try to find out why you're running into those situations. Oftentimes, it's a bug in your code, and you need to address that. But ultimately, that is one feature in Kubernetes that tries to keep your application up and running as much as possible. And then lastly, we also have the startup probe. This one shouldn't be confused with the readiness probe, even though they seem to be doing the same thing. I believe they likely should have given this a different kind of name. But ultimately, what the startup probe does, it simply prevents the liveness probe from being started in the process of starting up the application or the pod in general. And the reason is here that we could have applications that take extremely long to be brought up. For example, a minute, 2 minutes, 5 minutes, depending on what the application does. There are plenty of legacy applications that are not as efficient, that are not necessarily microservices, that are probably monoliths. We try to place them into Kubernetes, and therefore starting the liveness probe, if that's what you defined in your container definition, would just create additional traffic, and it would hold up on basically the startup time for your application in general. So that's the main purpose of the startup probe. Now, for any of those probes, we can choose from a set of different health verification methods. Any probe can use any health verification method available, so it's not really constrained. It really depends on the type of application that you have in place. And as I mentioned before, HTTP GET request, good option for web-based applications. There could also be a custom command. So if you want to run a command that you want to use to basically identify if the application is up and running, that's a possibility. There's also support for gRPC now, which was the latest edition of verification methods. So basically have a look at that and pick and choose depending on what you want to solve here. Now, for each of those verification methods, there's a set of default values and a default behavior at runtime. You can see there's a set of health check attributes, which come with the default values which control that runtime behavior. So for example, if you want to wait a little bit of time before you even start with running the first check, then you can change the value for initial delay seconds. There could be a certain threshold of errors of failures or success of failures that you may want to tweak. If you don't define any of those attributes, it will simply just go with the values defined in the default value column here. And just to give you the impression how this could look like in the definition of pods, you can see we don't have to come up with a new Kubernetes primitive. We will simply just add the corresponding probes to the definition of individual containers, as you can see here. Here we're adding a readiness probe that uses the HTTP GET verification method. So effectively, this will make a HTTP GET call to the to localhost on port 8080 on the root URL context path. So given that that would have to exist, basically tells you that you need to have some sort of HTTP server in place. Then here's one example for a liveness probe. In this case, we are using some bash commands to verify if a specific file being produced or populated by the application is being touched on, if it's been changed over time, as an indicator that the application is up and running. So the assumption here would be the application adds a new entry in that text file called heartbeat.txt. Say every like 20 seconds, it writes to it a new entry. And with this custom command, we basically verify if that file has been changed in the past minute. And then lastly, here's one example for the TCP socket connection. Here, we're just trying to open that socket connection on a specific port. So those are just the different combinations. Obviously, you can combine all of those probes together. One more side note that I would like to mention here. If you are somewhat lazy like me and don't want to basically duplicate certain values like the container port, you can also define them with the help of a specific name. And as you can see here, the name is HTTP port in my definition of containers. And then if I want to reuse that value, so port 8080 multiple times, I can simply just reference that port by name. That is one thing that is supported in Kubernetes. And with that, let's give this a try. This would be number 18 here. So for this one, I'll give you 10 minutes. Shouldn't take super long or shouldn't be super complicated. but it will give you some exposure to those probes in more detail. All right, so let's jump right into the solution here. What I'm going to do, I'm going to go one up, I believe. And then we will get started by basically creating a good starting point. Again, hybrid approach, keep that in the back of your mind, maybe useful. And that is what I'm going to do here. I'm going to write the starting point into this pod.yaml file. Alternatively, you can also check the documentation. And a couple of things we can remove again here. For example, this, and this, and this, to keep it as simple as possible. And then what I want to add here is two different portions. So what I could potentially do is to search for readiness probe. If I don't want to type this, it probably has a pod starting point, so my bad. But if you wanted to see something here, you can probably get a good starting point like this. We'll copy that, and then we'll just add it right here. So here we don't want to use the TCP socket configuration. We want to use HTTP GET. Oops. Then the path that we want to call, the port, which is going to be 3000. And then here we have some additional configuration. I'll remove that. And then we can basically duplicate that. Just showing you some ways to save some time during the exam. Okay. Here we'll actually use the same configuration, but the initial should be 5 seconds. And then here we want to use period seconds of 8. And I believe up here, it should be a different number too. And as I mentioned before, for any port that we want to reference multiple times, you can see we have like 3 different copies. We can effectively use a name assignment. And then basically duplicate that over here. So in the end, if the port needs to change, we only have to change it in one place, which is slightly more convenient. It's not a big deal, but ultimately it makes it a little bit more maintainable. So let's apply that change. And you can see it's in the process of being started. All right, it's running, and basically that is happening all in the background. I don't think there's a way to basically see when those calls are being made in any kind of log file or something like that. What we can inspect though, if you ever wanted to find out how a pod is configured, you can describe that object, and you will see that the different kinds of probes you may have configured with their configuration will be listed here as well. So that's super useful if you want to inspect them. All right, any more questions on the probe definition here? I'm just looking at my clock. We're basically running out of time, so maybe we'll just call it quits for today, depending on how many questions you have. All I have left in my section for the domain is to talk a little bit about the metric server, which we've already done. So I've shown to you the kube control top command, which is super useful if you want to basically inspect the current resource consumption on nodes and pods. I'll skip over that. It's pretty much what we've been talking about. By the way, there's a question or exercise here that you may want to go through. It basically lets you exercise the top command in more detail. We'll skip that one. It's not going to be super complicated. And then next up, probably more tomorrow morning, we'll be starting to talk about some troubleshooting techniques. In this context, we'll talk about troubleshooting techniques for pods and containers. And then tomorrow, we'll also talk about services and how to troubleshoot those. That will be happening pretty much at the end of the day during the course, probably last hour or so. But I think that's going to be exciting. So coming back to where we stand, CKAD curriculum. Let me see if I can find it right here. And if you click on that one, you will actually see we're almost done with application observability and maintenance. So we already learned how to do logs, debugging, troubleshooting, those kinds of things. And then tomorrow, we'll actually get started with what we have left in this course, which is going to be this bigger section, application environment configuration and security, and then the topic on services and networking. So that is what we're going to cover tomorrow. I would say tomorrow at the beginning, it's going to be a mixed bag of different kinds of topics. They try to reorganize everything into this one bigger domain. Doesn't really fit together necessarily, but it's one way to organize it, but that's how we'll go through it. And then lastly, I think the important topic here is going to be on services, as well as network policies and the ingress. And just as a heads up for anyone that was looking at the CK curriculum as well, the Gateway API is not being covered by the CKAD as of now. I would assume that it will likely change sooner or later, probably with the next bigger update of the CKAD certification. All right, any more questions you would like to address before we close for today? Now, I think it doesn't make sense to start with troubleshooting now because we'll probably run out of time, unfortunately. And for the person that was asking on the voucher code, so you get 30% off now with the code Ascend30. This has just been corrected by my contact at the Linux Foundation. So you should be good to go on that end. All right, if anything else comes up, or here's one question: how often do they update the exam? Multiple times a year. So the main update that happens every 3 months is the update of the Kubernetes version. So depending on when a new release is available, they will update the exam environment to that new Kubernetes version, which potentially could mean that certain functionality is maybe slightly different or something has been added. Any major updates, I would say, usually happen every 3 years to the outline. But usually this hasn't been changed since 2024, so it's been a while. And we are already in 26, so probably by the end of this year or maybe sometime next year, I would assume there will potentially be a new update. But keep in mind, your certification is going to be good for 2 years once you pass the exam. All right, I think that's all we got. With that, I'll give it back to Brittany, and I will see you tomorrow at the same time.
All right, thank you so much, Benjamin, and everyone who participated in today's course. This concludes day 2. We will see everyone tomorrow for day 3 at the same time of 7 a.m. Pacific. Enjoy the rest of your day. Goodbye, everyone. And recorded sessions are available as long as you have an active O'Reilly account.